Hello, hi everybody. I'm Flavio Castelli from Italy. Today, together with Rafael, my colleague, I will talk about how to make Kubernetes clusters smarter so that they can react to external inputs in an automated fashion. So let's get straight to the problem that we're trying to solve, which is a pretty common problem, which is you have a workload that is deployed and is offering a service. Let's say, for example, that you're running an e-commerce website, and then suddenly Black Friday happens and your website is no longer available because everybody is trying to buy things from your application, and there isn't enough hardware to run your web service. So what you can do now to solve this kind of problems? Well, if you try to tackle this problem with, let's say, a fixed approach, you try to calculate the right size of your deployment, then you will end up with two possible cases. Either you over-provisioning your infrastructure, meaning that during Black Friday, everything is going to be great, but during the rest of the year, you're going to pay a lot of money for resources that you're not actually using. Or the other way, you might end up under-provisioning your infrastructure. So maybe during the majority of the year, everything will just work fine. But when a special offer goes on, not even something as big as Black Friday, then your system will start to slow down, collapse, and you will end up losing a lot of money due to that. So trying to get this calculation correct and right is hard. It's way better to have a more flexible and dynamic approach to this problem. So there are two possible strategies when it comes to scaling applications. The first one is to scale an application vertically. So you just, you buy more expensive hardware, you have a more powerful CPU, a better hard drive, more memory, and then you deploy your application on top of it. You might think this is still, static, but if you think about having an infrastructure as a service running underneath your application, then you have a really nice set of APIs, and you can provision a beefy machine just for Black Friday, or you can provision more powerful machines for special offers during the rest of the year. And then when you don't need all this power, you just give it back to the infrastructure as a service, and you don't pay for it. You just stay on smaller application, on smaller hardware. So the biggest advantage of this approach is that you don't have to change a single line of code inside of your application. This is working really well if you have, let's say, traditional applications. You just buy expensive machine. We have always done that in the past, and that just worked fine without having to re-architecture everything. A different approach instead is the one of scaling an application in an horizontal way, which means that we have a spike of requests, and then we will just, as a result of that, we will provision more instances of our application across a cluster, across many machines. The biggest advantage here is that there is, let's say, potentially no end to how many instances you can scale. But on the other hand, you have to properly architecture your application in order to make it work in this context. And this is not something, so easy to take for granted. This has to be properly thought. And this is something that, for example, modern applications that are considering, themselves, that are designed to be cloud native, this is something that is done when designing these applications. So it's an approach that works really well with applications. So these are really generic concepts that we have always used in a traditional environment, but we are here today to talk about how to embrace these patterns also in the Kubernetes world. So now you have your web application for your e-commerce running containerized, and you're deploying that on top of Kubernetes. At the bottom of the stack, your application would be running inside of a Kubernetes pod, which is the smallest deployment unit for Kubernetes. Kubernetes pods they have limits. You can specify a CPU and a memory limit for each one of them. You can do that at the pod level, or you can do that, as we will see later on, at a higher level. So once you set these limits, it's like saying, I'm running that on a machine with this amount of memory and this amount of CPU. The biggest advantage here is that this is set in code. So if you want to scale your pod vertically, what you have to do is just edit this code, change the definition of a pod. You just go ahead and set a higher value for it, and your pod will have more resources just out of the blue. You can scale pod horizontally instead in another simple way. You just spin up a higher number of pods that are running your workload. There is the concept of Kubernetes services that is built into Kubernetes, and that makes the whole process even easier, because as soon as you spin up more pods running your application, you will have the problem of routing the incoming traffic to all these pods. But if you're using a Kubernetes service, this is going to act as a load balancer across all these pods. And if you want to do something, let's say, more fancy, you can even resort to use a service mesh for that. However, this is not going to be the topic for today, but all these concepts really match well with horizontal scaling. So to scale a pod horizontally, you don't have to actually, go and create more instances of a pod, because nobody's actually, creating pods manually. Everybody relies on using higher level abstractions that are provided by Kubernetes, such as replica sets that allow you to define through a dedicated field how many instances of a pod you want to have running. So you just change this number, and Kubernetes goes on and automatically takes care of that. A lot of people are also leveraging a resource of Kubernetes called deployment, which is built on top of replica set, and it provides even more features compared to replica sets, such as having certain rolling out strategies, being able to roll back, but the concept is still the same. So to summarize, if you want to scale horizontally pods, what you have to do is just change a single line of code inside of a definition of a replica set or a deployment, and then Kubernetes will take care of that for you. Now, we don't want to go out and do all these operations manually. What we want to do is to have something that reacts to a spike, an external spike, and just tunes all this value, adjusts the numbers of instances that we want to be running, or raises the amount of CPU and memory that a certain pod is going to use. We want to define a sort of a baseline, which is the minimum amount of resources that we are going to be running all the time. And then we want to have the system react in a dynamic fashion and scale up when there's a spike, and when everything is over, just scale down so we don't waste money on useless resources. To do all of that, however, we need to measure the impact of that external users, external factors are having on our application. We need to collect metrics, and for that there is a component of Kubernetes which is called the Kubernetes metric server, which has the purpose of collecting data, collecting information metrics from different pods, from the nodes, from the memory. It keeps track of a lot of kind of informations, and then it exposes all of that through an API. Now, someone might ask, why do I need to deploy this extra component on top of Kubernetes? Because I'm already keeping track of the metrics of my application by using something as Prometheus, for example. Well, that's a good question. Well, the metric server, as we will see soon, thanks to Raphael, is exposing an API that then is consumed by a series of open source projects. And this API is different from the one of Prometheus. The way the Kubernetes metric server is architectured is different from Prometheus. It's built for a specific purpose, which is slightly different from Prometheus. So to summarize, the Kubernetes metrics server is not mutually exclusive to Prometheus. They are both complementary. They have to be both running on top of your cluster in order to have your application metrics collected for your own purposes and to have these metrics collected by other software that Rafa is going to talk about. And with that said, I will leave the virtual stage to Rafael to talk more about that.
Thank you, Flavio. So as Flavio said, there are some components, open source components that can be used on our cluster in order to get advantage or take advantage of the metrics server and how it exposes this information. So one of the components is the vertical pod autoscaler. This is very tied to what we were talking before about vertically scaling your infrastructure. So what the vertical pod autoscaler will do will be reading this information from the metrics server, so it knows what resources your current pods are using. And one of the main components of the vertical pod autoscaler is the so-called recommender. This is a component on the vertical pod autoscaler that will annotate your resources in a way that will tell you what it recommends for you based on the current usage of your resources. So in terms of CPU and memory. So basically what you can do with the vertical pod autoscaler is two things. One is just let it you recommend what it recommends for you in terms of CPU and memory allocation, and the other is actually applying that. So let's see how it works. This is a very simple example of the vertical pod autoscaler. It's not much more complex than this. Because basically what it will do is, as I said before, look at the current resource allocation and see if it needs to change those in a way in which it will fit better the current resource usage of your deployment. So in this case, the update policy is auto, which actually means that it will work in a way in which it will see if the recommender matches what it has actually. If not, it will kill the pods that don't match the recommender status. And if that happens, Kubernetes will actually recreate those pods out of the box. This is the regular Kubernetes operation because you usually are using higher level abstractions, as Flavio said before. And then when it happens, when it recreates these resources, these pods, the vertical pod autoscaler has another component that is the admission controller that will actually set these resources on creation for these new pods. So basically what happens is that the vertical pod autoscaler kills these pods that are not matching the recommended status, and when they get recreated with the recommender status. So basically that's the way it works, because Kubernetes doesn't allow at the moment to change these resources like when they are running. So this will change in the future, and when that happens, the vertical pod autoscaler will also allow you to change this in flight, let's say. Then we have the other component called the horizontal pod autoscaler that is also related to the other concept, that is, instead of changing the resources of my deployments, of my deployed services, what I want to do is to create more copies of them. And basically, the horizontal pod autoscaler works in the same way as the vertical one. It reads the metrics server information. This is information, as Flavio said before, only meant to be consumed by this kind of components. The metrics server is not going to have time series like Prometheus, for example, something that you can actually look into the very past, let's say. It's only for knowing what's the latest status of your infrastructure. So the horizontal pod autoscaler will alter the number of replicas automatically on replica sets, deployments, and stateful sets. Again, this is a component that only does this, and Kubernetes will do the rest. So right now, today, if you change manually your replica numbers on a deployment from 3 to 5, Kubernetes will actually create those pods out of it, or the other way around. If I have 5 and I set 3, then it will remove 2 of them. So the horizontal pod autoscaler is only patching this part of the resources on replica set, deployment, and stateful sets. This is one example of the horizontal pod autoscaler. As you can see, you can name it as you want. The important part here is the spec part, where you can say what is the target that is referencing. In this case, it's referencing a deployment called my application. And you can actually set what are the specs, what are the mean replicas that you want of this deployment, the max number of replicas, and also the CPU utilization percentage, for example. We will look more into how to use other metrics later, both for VPA and HPA. But this is how it works. You can configure more things on the VPA. For example, I didn't say that you can also configure what is the maximum and minimum usage of CPU and memory, so it won't kill your all your pods. It won't consume more than you want on your deployment. And so a word of warning when you are using both of them at the same time. So you can use both of them, but you cannot use them together using the same set of metrics, because this means that they don't expect the other one to be acting on their back. So for example, this will alter the metrics altogether if both of them are working on the same set of metrics, and then they can, fight each other. In that sense, you could have the vertical pod autoscaler for a certain set of resources, the horizontal one for another set of resources. That's perfectly fine, but you shouldn't use both if you are relying on the same set of metrics for both. And then how to instruct both. You can use metrics from the metrics server. This will get the CPU and memory usage from the different kubelets in your system. But you can actually, this is not realistic in the sense that not everything is CPU and memory usage, right? There are really, really interesting custom metrics that are application specific, like for example, mean response time, size of queue on our queue system, what is the error rate of our services, things like this. So for this, you can actually have another custom metric server that basically implements a basic one. This is for the custom part of metrics. The metric server has two kind of custom metrics. Let's say this is the custom one, and then this is the external one. We will talk about the external one in a second. But the custom one is basically you have a simple template of the metric server, and you are able to export different kind of metrics that your HPE and BPA can use from this. These are exported metrics. So for example, you can also leverage Prometheus through an adapter that exposes this as custom metrics. And then you just configure VPA or HPE to use those. There is also the concept of external metrics, which is basically using some external system. This would be different from the custom ones that we are talking about here, because the custom one is something that is exported inside the cluster. The external one is something that is completely outside of the cluster. But you can still consume those and use those as well. And then if we have the horizontal pod autoscaler, for example, as an example with custom metrics, the interesting part here is at the right-hand side. You can see the metrics part there, where you can actually say, based on my custom metric, for example, my app request per second, I want an average value of 2. So if it increases over time, the horizontal pod autoscaler will create more replicas out of it until everything establishes and everything is constant, more or less, and then it will do the same thing, basically replicate, bringing down the replica number of your service. So this is all nice, but what happens when you run out of resources? Because pods are in the end running on nodes. Computing nodes or physical nodes has also constraints. They have a limited number of CPUs. They have a limited number of memory, and maybe you run out of resources. So when you are horizontally scaling, there is no more space to run the new pods. The scheduler of Kubernetes won't find a new home for your new pods. Or when you are vertically scaling, you will just run out of resources on that machine where you are trying to vertically scale your deployments. So for this, there is the cluster autoscaler. This concept is basically setting a baseline where you have a minimum number of worker nodes that you want always to be present and always part of the cluster. These nodes are never going to be removed. And when Kubernetes detects with the cluster autoscaler, this is yet another component that you can deploy on top. We'll check if there are no more place for new pods. We will talk about that in a second. And also we'll remove worker nodes once they are no longer needed. Again, when it considers that they are underutilized, it will just remove those worker nodes from your pool of worker nodes of the cluster. So when you are scaling up, the cluster autoscaler will monitor which pods are unscalable due to insufficient resources. So there are different reasons why a pod couldn't be created, but the cluster autoscaler is only monitoring the reason when there is no resources left for creating those pods. It will wait a little until everything establishes, so the pod will be unscalable for a little period of time. This is all configurable on the cluster autoscaler, and then what it will do will basically create a new worker node. So it will then wait a little more until the new reconciliation. So this is basically how the scaling up works, and the scaling down is very similar in that it will monitor what is the utilization, the mean utilization of each node, and then if it's the case, if it's underutilized some of them, it will go by one and waiting, providing some time for everything to recover and terminate unneeded and underutilized working nodes. So how it works, cluster autoscaler is hands-off of your infrastructure in general. The way it works is by leveraging the scaling groups provided by all major infrastructure as a service, public clouds, or for example, OpenStack. What it actually do is basically change the number of scaling groups. How do you join these nodes afterwards? It's completely up to you. Actually, also the cluster autoscaler won't remove the node from Kubernetes once it removes the infra. This is something that you should do. But in general, it's automated in the sense that you can just see everything on the aftermath, right? It actually did its work when it was needed. And there is also an interesting approach on the cluster autoscaler because right now, as I said, is very tied to major public cloud services or OpenStack. And the other approach is to use Cluster API, which is a project that allows you to define your infrastructure in a declarative way and use Cluster API as yet another backend. So you would have the scaling group backends, let's say, for its public cloud, major cloud, private cloud, but then also the Cluster API project, which you can plug with complete different components. And basically, this will mean that it will modify the Cluster API resources, and then Cluster API will do its thing, basically creating these new resources somewhere else in the way that it was defined on Cluster API itself. But this is all is fine. I mean, we can scale based on CPU memory, on our own metrics. We can actually also scale nodes themselves. But there is a really important thing here, which are the application design considerations, right? Because if our application is not ready for these kind of changes, it's not ready, to be removed completely from a node, created somewhere else. If it's not playing nice with these kind of changes, then nothing will work. I mean, Kubernetes will do the right thing, but our application won't be ready to do this kind of operation, right? So one thing that we should wonder is the application microservice oriented? Because if it's not, then the entire application will be scaled in and out. This means usually higher time rates in order to start, because a monolithic application usually has more things to do when starting. That's something we need to keep in mind. And also, there is also something interesting when we are talking about microservices, because maybe we don't have the full picture in mind when we are changing the replicas of our services, or we are seeing small peaks on our services, because depending on how these microservices connect to each other, it could happen that some middle microservices, some middle microservice will have a much higher level of rates. Let's say it's going to get more requests based on other services. So this will play really nicely with the way that we design, with the way that we explain the HPA and BPA, because basically this means that our microservices will, in a complete automated way, auto-scale themselves, which is actually pretty nice based on this set of metrics. And also, if your microservice or application relies on something node specific, let's say that you're using some host path or some storage that requires something from that specific node, you have to to keep present that when, for example, the VPA kills the pod and Kubernetes recreates it, it will get rescheduled probably somewhere else. So you need to take all these things into consideration when designing your application, so it will play nice with these technologies. And of course, Kubernetes is in the silver bullet in the sense that it can help us with many things, but it provides the foundations in order for all these things to work in an automated way. But of course, it cannot help us with absolutely everything. It won't magically make our application scale up or down, in the sense that if our application is not designed for the use case, we will have problems in any case. There is also some specific use cases that we are going to look into in a moment. So following this line of thought, we also have different applications are slightly different than what we could say they are not stateless. Let's say it's not about changing the number of replicas and we are done. Some applications, especially the ones that have the concept of cluster themselves, let's think about the database, for example, MariaDB. When you need to scale it in and out, you need to add more nodes into the cluster. So the whole application as a whole has the concept of how many nodes do I have? So for this kind of operations, you actually need to perform some kind of logical operation before you try to join another instance or to remove an instance, for example. As I said, one example is databases, but we can find other examples as well. So in this case, the way that Kubernetes is going is by using operators. So an operator on Kubernetes is an application itself that runs on Kubernetes and has a reconciliation cycle, let's say. It's all the time looking at the things that it needs to do for everything to be fine, let's say, everything to be, let's say that the observed status is actually the same as the specified status, the status that the user wants. So the goal of operators are usually to simplify the lifecycle management of a workload. If I have, for example, an etcd operator, etcd is a key value store that has state, is stateful, and I want to add another node, I have to do some things basically the same as I would have to do with MariaDB, for example. And with an operator, usually the operator defines a way to define an etcd cluster in this case. So I can basically tell the operator, I want a new etcd cluster, and the operator will take care of creating the pods, for example, on Kubernetes, and make sure that everything makes sense. If it needs to perform some kind of cluster-wide logic on etcd, it will do this logic in a way that it's, it has all the operational knowledge about etcd, right? So it will actually work. And then when I want to even change the replicas of etcd, I can actually do that as well. So I could say that I have 3 replicas and I want to change that to 5. And if this operator has this logic baked in, then it will just do the right thing. It will grow the number of etcd pods, for example. It will join these new pods on the cluster itself, so everything makes sense. So the operators are actually helping us in running these complex applications on top of our cluster. But of course, these operators are not consumable by HPE. They are complete different matters. So one thing is how HPE or VPA are able to change the resources that we have on the cluster at the moment. And the other is how something that is like an operator that has some logic baked in, some specific operation logic for a specific application can replicate or can scale up or down your application. So these are complete different things and we shouldn't mix them. And that's it from my side. So if you have any questions, please feel free to ask them. We'll be really happy to answer them. Thank you.
Thanks a lot.